Swayam Prabha. Digital India. Educated India.
Now earlier there was a question which I think was regarding this circuit, saying if there is yet another current source here, 3 milliamp, what happens? So this is quite simple. This 3 milliamp and 10 milliamp are in parallel. It is like having just a 7 milliamp current pointing downwards. Okay. So instead of 10 milliamps, you have 7 milliamps. Now the contribution of the current source, so this was minus 21 volts. So instead of that, it will be in proportion. Okay, minus 21 volts times 7 by 10. That's the meaning of linearity, right? So you can calculate how much this is. This will be minus 14.7 volts, I believe. So instead of adding minus 21 to 7, you have to add minus 14.7 to 7. So the net voltage will be minus 7.7 volts. Okay. This is fine. Any questions? Okay, so now we have discussed the Thevenin's and Norton's theorems. They are very, very useful and they are used very frequently for representing circuits at two terminals. Okay, and this happens all the time. You design some circuit, it's very complicated, but it has two terminals available to the outside world, and what you have to do is to give an equivalent picture to the user, and this will do exactly that you will get with the Thevenin or Norton equivalent circuit, which is very simple. You will get the equivalence of the circuit at those two terminals. Okay, you will not get an internal picture of what is happening, but at those two terminals, the behavior of voltage and current will be equivalent to that of the original circuit. Okay. There is a question on where to use Norton's theorem. I guess the question probably is which one to use, Thevenin or Norton, and that's entirely based on convenience. Okay, sometimes you use Thevenin's theorem and sometimes you use Norton's theorem. In fact, there is an interesting thing here that we can discuss briefly. So now, like I said, any circuit. So there is also another question, what is the proper condition for Thevenin and Norton? I guess what is meant is that what kind of circuits can be represented by Thevenin and Norton. And that I wrote out here. So this is exactly the condition. Any two-terminal network with linear elements and independent voltage and current sources. If you have a circuit that is like this, then it can be represented with either Thevenin or Norton equivalent circuit. Okay, so if you have nonlinear elements, you cannot do this. Okay, and also one thing which I mentioned last week as well, that if you do have dependent sources in this, that is okay, but it should be dependent only on quantities inside N. Okay, you cannot have them externally controlled. Now, like I said, any any circuit with only two terminals available can be equivalently represented at the two terminals using either Thevenin or Norton equivalent circuit. Okay. So now let me say this is my circuit. Okay, this is now an extremely simple circuit. I have a voltage source. Okay, now what is the Thevenin equivalent of this and what is the Norton equivalent of this? I have only a voltage source. Please try to reason out and answer this question. This is not so much of calculation, but reasoning out. I have only a voltage source connected to terminals 1 and 1 prime. Okay. So what's the Thevenin equivalent of this and what's the Norton equivalent of this? I think that answer for Thevenin equivalent is very clear. It's the same as this circuit. Okay, with RTH equal to 0. VTH will be 10 volts and RTH will be 0. Okay. But what is the Norton equivalent of this circuit? Yeah, again I've got some answers saying either the current will be infinite or it doesn't exist. All these are correct. First of all, there is also a question why the RTH of this is 0, and that's quite simple. So in this you have a single independent source and that you set to 0. Okay. So you make it 0 volt, which is a short circuit, and then you look into 1 1 prime. So what you see is a 0 ohm resistance. Okay. So RTH equal to 0 for this, that is pretty clear. Okay. Now the Norton equivalent doesn't exist because IN is VTH by RTH, and if RTH is exactly 0, if it is non-zero then you can find it. If RTH is very small, you can find this IN, which will become very large. But if RTH is 0, this will tend to infinity. Okay. That is, you have an infinite current and across it you will have 0 resistance because Rn, which is RTH, is 0. Okay. Now, and this infinite current through the 0 resistance can give you some voltage, in this case 10 volts. But this is really a useless representation. Okay, when you have infinities in the circuit, you can't calculate anything. But I am just making the equivalence here. The way to imagine it is, you imagine some resistance in series with this voltage source and take the limit as it goes to 0. Okay. So my point here is that while in general any circuit can be represented by either Thevenin or Norton, it is possible that one of them doesn't exist. Okay. So one or the other will surely exist. But if you have a pure voltage source between terminals 1 and 1 prime, the Norton equivalent doesn't exist because you cannot short circuit and find the current, or in other words, if you short circuit it, an infinite current will flow. Okay. Similarly, if you have a pure current source between the terminals, one milliamp, 1 and 1 prime, this again, the Thevenin equivalent doesn't exist and the Norton equivalent is the same as this. It's just a current source. Okay. Now there are a couple of questions. First of all, if we reverse the case, we can get any voltage. That is exactly the point here. It is indeterminate. Okay. So when you have infinities here, it's indeterminate. Now the other question is, if you have a voltage source and a current source, do you have a Norton's equivalent? If you have a voltage source and a current source, then in parallel, the result is just a voltage source. Okay. This mentioned a few times before. If you have a voltage source in parallel with anything, okay, whether it's a current source or whatever else, it is the same as the voltage source itself. Okay. Whether you have a current source or not, it doesn't matter. The only thing that it will change is the current through the voltage source. Otherwise, nothing will change. Okay. So clearly, this is a voltage source, and there is no legitimate Norton equivalent circuit for this one. Okay. So I hope that part is clear as well. So there can be degenerate cases where one or the other equivalent circuit doesn't exist, but at least one of them will surely exist. Okay. And again, somebody asked about the application of this theorem. As I said, it is widely applicable. The basic point is to abstract out all the details of a very complicated circuit. You have a very complicated circuit with lots of components. Instead of using all of that in every circuit analysis, if you are interested in the behavior only at two terminals, you can use either the Thevenin or Norton equivalent circuit. Okay. Any other questions? So again, there is some confusion regarding the load. This equivalence is independent of the load. Whatever you load you connect to it, the behavior at 1 and 1 prime will remain the same as in the original circuit. Okay. So if you want to find the effect of the load on the original circuit, you instead connect the load across the Thevenin equivalent circuit and you will find exactly the same behavior. Okay. So now that we have discussed the Thevenin and Norton theorem, let's move on to another very powerful theorem, which is also used widely. It's mainly used to get more theorems out of circuit behavior. Okay. Now let's say we have some circuit. I will show arbitrary branches. I don't really care what the branches are. Okay, they can be any elements. And I will number the branches, let's say 1, 2, 3, 4, 5, 6. And I will label the voltage of every branch. V6, and then I'll also label the currents consistent with the passive sign convention. I1, I2, I3, I4, I5 and I6. Okay. So now, basically I have a circuit with, this I've shown with 6 branches, but any number of branches is okay, right? So now let's say we compute the sum of power in all the elements, that is sum of Vk over all branches. What do you think this is going to be? I mean, please give me a guess. Actually, there are many people who are still asking questions. I will deal with them soon after I deal with this particular thing. That is, in this particular case, I sum the power in all the branches, V1I1 plus V2I2 plus V3I3 plus up to V6I6. What is it going to be? Now it turns out that this number will be 0, okay, and this is known as conservation of power, okay. Now this conservation of power, what it means is that if you have a circuit and if some sources are dissipating power and some others will be generating power, okay, whatever power is dissipated has to be generated in some part of the circuit, okay, so there is no other external source of power, right? So we have only electrical variables here and electrical connections between elements. So whatever power is generated in some elements will be dissipated in other elements, or whatever power is dissipated in certain elements has to be generated in some other elements of the same circuit, okay. So that is what this statement means, that power is conserved in a circuit, okay. Now this also can be proved, and this can be proved basically using only Kirchhoff's voltage law and Kirchhoff's current law, okay. Now this is completely unrelated to what kind of elements we have. It could be linear, non-linear, whatever, but as long as our elements obey KVL and KCL, which is basically a fundamental property of the circuit, this conservation of power holds good, okay. So in fact I would strongly encourage you to try and prove this using only KVL and KCL, okay, and I will give you a hint. So let me not name them N1, 2. I will label these nodes N0, which is the reference node. You can consider this to be the reference node, it doesn't matter which one it is. And NA, node NA, node NB, and node NC. Okay. So you can try to prove this by making these products VKIK, that is V1, I1, V2, I2, etc. And this V1, I1, V1, V2 and so on are the branch voltages. Okay. Now you try to represent these branch voltages in terms of the node voltages, that is VA, VB, VC with respect to the reference node. Okay. And then you group all the terms containing VA and VB and VC together, and then you use Kirchhoff's current law. You will be able to prove this. Okay. So please take it as an exercise and do that. Hopefully you will be able to do it, otherwise we will discuss it later. So for this you have to represent branch voltages in terms of node voltages and group the coefficients of each node voltage, and then you will be able to pretty much immediately see the answer. Okay. So I will stop with this discussion here. We'll continue with this in the next lecture. But there were a few questions regarding Thevenin equivalent circuit. The first one is, what do we do when we have dependent sources? Now, dependent sources you find it in exactly the same way as we did with resistors. Okay. Now with resistors, what we did was to use the resistor formula to calculate the resistance. But in general, if you have any network with two terminals, let's say 1 and 1 prime, the way to find the resistance looking into 1 and 1 prime is to apply a test voltage, V test, and analyze the circuit. In case of Thevenin's theorem, whatever is inside will be nulled. All the independent sources will be nulled. And you find I test. Now because you have a single independent source V test, this I test will be proportional to V test. So the Thevenin equivalent circuit will be Thevenin resistance, will be V test by I test. Okay. Now this is true whether you have dependent sources or not. Now when you have resistors only, sometimes you may be able to use the formula for series or parallel combination of resistors. But in general, even with resistors, this is the method to use. Okay. So let me take a very simple example again. This is a voltage controlled current source whose value is, let me call this Vy, and the value of this is Vy divided by 2 kilo ohms, or basically 0.5 millisiemens times Vy. Okay. Let's say this is 10 volts. So how would you go about doing this? You have to find the open circuit voltage, which of course you do by in the normal way, 1 prime. You do circuit analysis to find out the voltage across this. Okay. And you have to also find the Thevenin resistance. For that you set the 10 volt to 0, so that becomes a short circuit. We have 5 kilo ohms here, and we have Vy, and all these things will remain exactly the same. Okay, you don't change anything in the dependent source. Then you apply this V test and find I test. The ratio of the two will give you RTH looking into this. Now this is a very simple circuit, but whatever arbitrary connection of dependent sources you have, you can still follow exactly the same procedure. Okay, I hope this is clear. So the procedure is exactly the same. You have to find the resistance between 1 and 1 prime. If you are given a black box, let's say in the lab, and asked to find out the resistance between 1 and 1 prime, what will you do? You will apply some voltage across 1 and 1 prime, find the current that flows through it, take the ratio, or you force a current from 1 prime to 1, or see the voltage that is developed across it and take the ratio. Okay, so that's how you do it for any circuit. Now it just happens that if you have only resistors, you may be able to take some shortcuts. Okay. Now the other question was, somebody said, how do we give the direction? I'm not sure what is meant by this. Maybe what is meant is the direction of the direction of the current source. Okay, so when you find the Norton equivalent circuit, you will short circuit the output from 1 to 1 prime, and you measure the current flowing from 1 to 1 prime. Okay, so that gives you the direction, right? So if the current is actually flowing from 1 to 1 prime, then inside you will have a current source like this. Okay, if in the short circuit current is flowing that way, then inside ion will be like that. If it's in opposite direction, then ion will also be in the opposite direction. Okay, so there is no confusion here. Now another question is, can source transformation be applied if the network contains nonlinear elements? Now, like I said before, the part that you are transforming has to contain linear elements. So what I mean by this is the following. So I have taken the example of this network N with independent sources and linear elements, and linear elements includes the resistances and controlled sources, with the only condition that the controlled sources have to be controlled by something inside N, some branch voltage or branch current. Okay, and you have 1 prime. Now the part that you are transforming, this has to be linear. Now if you have nonlinear elements elsewhere in the circuit, something like this, then that's okay. This is not what you are transforming. So whatever I have shown inside the red box, that is linear, and that can be represented by this Thevenin or Norton equivalent circuit. And the source transformation means that you either you go from voltage to current source representation, which means that is also applicable only to linear circuits. Okay. Any other questions? Okay, so if there are no more questions, please try to do some of the things that are indicated, that is trying to prove the Norton's representation, that it is valid for any circuit. That's one thing you can do, and you can follow the lines of what we did for the Thevenin representation. And you can also try to do the other one, that is try to prove conservation of power for any circuit using KCL and KVL. Okay. Okay, there is another question. Again, I am not clear of what this question is. It says, across a single element, if there are two voltage sources of same magnitude, superposition fails in finding the current in the resistor. The question is, are the voltage sources in series? Is that what is meant here? Now see, if you have two voltage sources of same value in parallel, okay, now this is the same as a single voltage source. So that is one thing. Now if you insist on using superposition, you will get a degenerate answer. Because if this is V and this is V, and you have to set this to 0, then you have to short circuit it. Okay, so you'll have infinite current here and some voltage across the resistor and so on. Okay, so this is basically a degenerate condition, and you can't represent things like this. Okay,